Hi everyone, this is Mrs. Snowbeck. Today we are going to do Unit 3, Lesson 5, Applications of Sinusoidal Functions. And by the end of this lesson, we hope that you can solve some real-world sinusoidal application problems, basically word problems. Number 1. A Ferris wheel has a radius of 12 meters and makes one complete revolution every 12 seconds. The bottom of the wheel is 2 meters above the ground. Let t equal 0 when the rider is at the 3 o'clock position. I'd like to start by drawing a picture. And so picture a Ferris wheel. The Ferris wheel cannot touch the ground, otherwise it's not going to be able to turn. So we have some kind of a Ferris wheel, like so, and it is 2 meters off the ground, and the radius is 12 meters. So imagine you get on, there might be like some little steps or something to get on, and you get on and you go around to the 3 o'clock position, which would be over here. This would be the 3 o'clock position. And at that point, let's think about what is the coordinate at that point. Well, if we think about 0, 0 being down here at the ground, at this point, let me put it in red here. At this point right here in red, the coordinate would be over 12 and it would be up 14. Why 14? Because we have 12 plus 2. So the coordinate at that 3 o'clock position is 12, 14, and that's going to be the starting position of the ride. So let's say the ride starts up and you're going to go in a counterclockwise motion. And by the time you get up here to the top of the Ferris wheel, let's think about what's the coordinate up there. Well, if this is 0, 0 down here at the ground level, that position, think about this being 12, it's going to be up 2 plus 12 plus 12, and it's going to be over 0. So that position is going to be 0, 26, over 0, up 26 feet. By the time we get over here on the left, you're going to be at a coordinate that is negative 12 and up 14. And by the time the Ferris wheel gets down here at the bottom, you're going to be over 0 and up 2. You're going to be 2 feet off the ground at that bottom position. So the first thing I always do is I always draw a picture with a problem like this, a word problem. So for some reason, pictures help me get straight in my mind what's happening. The second thing I usually like to do is graph the situation. Now I kind of read through the questions and I noticed down here in the last question, it wants to know how high is the person at 12 seconds into the ride? How high is the person at 5 minutes into the ride? So I think our focus here needs to be height on the Ferris wheel at certain times. So our two axes, this one on the x-axis, I'm going to label that time in seconds. Each revolution is 12 seconds. And then the other thing that's going to be important is the height. So I'm going to label this one height. And it will be measured in meters. All right, now let's think about how long this ride is going to take. 12 seconds gets me one time around. So I think what I'll do is I'll count by threes. So this is going to be 3, 6, 9, 12, 15, 18, 21, 24. That would be 2 revolutions. And then think about the height. The lowest I'm ever going to be on that ride is 2, and the highest I'm ever going to be is 26. So I need it to go up to at least 26. Half of 26 is 13. Maybe I'll count by 2s. So we have 2, 4, 6, 8, 10. So I'll just go like 6 and then 12, 14, 16, 18, 20, 22, 24, 26 meters. Then we want to start placing our dots. So after 0 time has passed, think about where are you on the ride? Well, this is our starting position. I'm highlighting it in blue. That's where 0 time has passed. So at 0 time, our height is 14. I'm going to put a dot at 0, 14. Then after 3 seconds, because remember it's going to take 12 seconds to get all the way around, so 12 divided by 4 sections, each section is going to take 3 seconds. So after 3 seconds, I'm going to be 26 feet. I'm going to go from here up to here, and I'll be 26 feet off the ground. Put a dot there. After 6 seconds, I'll be coming back down, and I'll be at 14 again. After 9 seconds, I'll be at 2 feet off the ground. Remember, it can't scrape on the ground. You'd wreck the Ferris wheel. And then 3 more seconds gets us back to the starting point. So after 12 seconds, we're back at 14. Here is the beginning of our graph. Can you see that it kind of looks like a sine curve, or possibly a cosine curve that's had a phase shift? We'll have to see. Let's continue that pattern. So it's going to go up to 26, down to 14, down to 2, and back up to 14. And we'll graph in 2 periods. In fact, we're actually doing part H of the problem right now, where it says sketch the graph of 2 revolutions or 2 periods. So we have done that. Let's look at the midline. Where is the midline? Well, I'm noticing right across here is the midline, and that is at y equals 14. The other question that I'm wondering is, what's the amplitude? So think from that midline up to the maximum. How far is that? Well, what I would do is I would take 26 minus 14. 26 minus 14 is 12. Do you think that's a coincidence? Think about what is the radius of the circle. So 12, and we can even say meters, is the amplitude. That's going to be the same as your radius. The period, how long does it take to repeat? Well, it's going to repeat every 12 seconds. This is a pretty fast Ferris wheel. We're going to be whipping around. The midline we just talked about is at y equals 14. It keeps coming back to that spot that's 14 feet above the ground. Next, we need to find k, and k affects the period. And so I want you to remember this formula for sine and cosine. The period is 2 pi divided by k. Well, we already know the period is 12 seconds. So imagine 12 equals 2 pi divided by k. Let's try to solve this for k. So I'm going to have to get it off the bottom of the fraction. So I'm going to multiply both sides by k. These will cancel out. And then I'm going to have to divide by 12. And what happens is these cancel, and k equals 2 pi over 12, which reduces to pi over 6. It's kind of tight in here, but I'll squeeze it in. Pi over 6 is k. Let's think about maximum height. What's the highest we ever get on this Ferris wheel? 26 meters. What's the lowest we ever get? 2 meters. And can we write the equation for this graph? First, think about, does it look like a sine curve or a cosine curve? It starts right on the midline. This point right here, I'm putting a big red dot there, that's right on the midline. And so I think this is like a sine curve. It's not starting above it like a cosine curve would. Here is our equation with the rectangle around it. So let's try to write it. So it's going to go like this. It's going to go y equals, A is the amplitude, which is 12. So 12, is it negative 12? Is it reflecting over the x-axis? No. Next is k. So next we would do pi over 6, and then usually it's x, and then minus the phase shift. This has no phase shift, so we could put a 0 there if we want to. And then the midline. So it's up 14, so plus 14. Now the only thing that you can simplify here is you don't really need the minus 0. So I'm just going to go down here because there's not much room. You can rewrite this y equals 12 sine, and you can shift those parentheses to look like this, pi over 6x plus 14. You don't really need that x minus 0 in parentheses. Now for the final question. Part I, how high is the person after 12 seconds? Well, 12 seconds, if he starts at the 3 o'clock position and does 12 seconds of the ride, he's going to be back at the 3 o'clock position. So at 12 seconds, he's going to be, or she is going to be at 14 meters high. Now, how far up will that person be, or at what height will that person be after 5 minutes? Okay, by the way, can you imagine going around at 12 seconds per revolution for 5 minutes? I don't think you'd feel very good. 5 minutes, let's think about this. 5 minutes, each minute is 60 seconds and our time is in seconds. So 5 times 60 is 300 seconds. Let's figure out how many revolutions is that. So 300 divided by every 12 seconds, that is 25. That means we're going to go exactly 25 revolutions in 5 minutes. And so we'll be back to the exact starting point. So at 5 minutes, our height will also be 14 meters. We'll be right back where we started at the starting point. So just to finish off our list over here on the right, number 1, draw a picture. Number 2, graph it. And then number 3 is find the amplitude and the midline, etc. We'll do that last. Number 2, the tide on the Miramichi River in Miramichi, Canada has a range of 8 meters. Right away, I had to kind of stop and think about this, and I thought, there's a tide on a river, because I've only really thought about tides being in the ocean before. But this river probably flows to the ocean or from the ocean. And so as the tide comes into shore, it's going to go up the river as well. And so it's going to affect the height of the water in the river. And the range is 8 meters. So at its lowest to its highest, it's going to change by 8 meters. At time t equals 0, the tide is midway. At 4 hours, the tide is low. The tide completes 1 full cycle in 16 hours. Let's label our graph. Let's have the x-axis be time in hours. And let's have the y-axis be the height of the river, and let's do it in meters. Think of it as meters above sea level. Now, at time equals 0 to time equals 16 hours is going to be 1 cycle. So I think counting by 4s makes sense because it says after 4 hours the tide is low. So I'm going to go by 4s. Go ahead and label your x-axes by 4s. And it says you're going to draw the graph for a 32-hour period, so make sure you at least go up to 32 hours. Then think about, what does that x-axis represent? Well, the x-axis represents sea level, basically. Or I should say the average sea level of the river as the high tide and low tide occur. So at time 0, we're at the midway. So let's just put a dot right here. And then after 4 hours, it's at low tide. But you have to think about the range. The whole range from low tide to high tide is 8. So that means at its lowest, it's going to be at -4 meters below the average sea level. And at high tide, it's going to be at +4 meters above. That has a range of 8. So after 4 hours, we're down here at low tide. Then it's going to start rising again, and 4 hours later, it'll be back to the midway mark. And then after 4 more hours, we're going to have high tide. And then after 4 more hours, back to midway. And voila, we have the beginning of a graph. It's kind of looking to me like it's going to be a sine or a cosine graph. Let's finish off the 32-hour cycle. So I'm just going to fill in the rest of my graph. And it will look like this. Kind of pretty. Now, I guess we've done part A. We've graphed the 32-hour period. So let's go to part B. Now it says write an equation to represent the height of the water with respect to time. So I want you to first think, what kind of curve is this? Is it a sine, a cosine, a tangent, a cotangent, a cosecant, a secant? What is this thing? I think it looks like a sine curve or a cosine curve. And since it's starting right at the midline, because think about the amplitude, this and this are the same, I think this looks like a sine curve that's been reflected over the x-axis. Instead of starting going up, it's starting going down. So now I want you to think about that equation. Y equals a sine k x minus b plus d, and think about all these different values. So let's think about the amplitude. I think you can eyeball it here and know that it's 4, but I want to show you a little formula in case you need it in the future. So to find A, you're going to take your max minus your min and divide by 2. So in this case, 4 minus negative 4 divided by 2, that's really 8 divided by 2, which is 4. So our amplitude is 4. Now it might be negative since it's reflecting over the x-axis, so keep that in mind. Let's think about k. To find k, think about the period formula for sine and cosine. Normally the period's 2 pi, but you have to divide by k. So in this case, we know our period is 16. So 16 equals 2 pi over k, and we want to try to solve this for k. So get k off the bottom of your fraction, and then divide by 16. This is kind of messy here, but you can see k equals 2 pi over 16 or pi over 8. So this is a, this is k. Is there a b? Is there a phase shift? I'm going to say no, because this point, this starting point, is right on the y-axis. I don't think it's shifted left or right. And is there a midline shift? Well, a little trick for finding what the midline is instead of subtracting the max and the min, you add them. So you take the max plus the min and divide by 2. And so we're going to take 4 plus negative 4 and divide by 2, which is 0, over 2, which is 0. So the midline is at y equals 0 still. In other words, d is 0. So I think we have everything we need to write the equation. And so here we go. I'm just going to put it up above the map. So it's going to go y equals. Now the amplitude is 4, but it reflects over the x-axis, so it has to be negative 4. Sine. Do we have a k? Yes, we do. Pi over 8. Then x. And then minus b, which we don't have a phase shift, and then plus d, which is 0. So I'm just going to put the parentheses around the pi over 8 x. Generally, that's what you do if there's nothing behind the x. And there it is. Fancy equation for the tides on the Miramichi River in Canada. Crazy how that can be represented with a sine function. Last one. The average monthly temperature in Juneau, Alaska is in this table. Let January be T equals 1. Using the data below, answer the following questions. Part A, draw a scatter plot of the data for one period. Think about a period for the temperatures in Juneau, Alaska. How long will it go before the temperatures start their cycle over? Well, just like here in Minnesota, it's going to be 12 months. Every 12 months, the cycle is going to start over. They already have the graph labeled for us, and they said let month 1 be January. So at January, the temperature is going to be about 24.2. So I'm going to go 1, and then 24.2 is approximately there. And then at February, it's about 28.4. And then at March, it's 32.7. Go ahead and plot these points. So pause the video, plot these points, and I will also. Okay, so here are my points plotted. I want you to remember that this is January at number 1. And then if I plot another point out here at January again at 24.2 would be approximately right here on the 13th month. So this represents one period or one cycle. Part B, give the maximum, minimum, midline, period, and amplitude. Here we go, one at a time. Maximum, looks like it's in July at 56 degrees. Max is 56. Minimum temperature, looks like it's in January, 24.2 degrees Fahrenheit. the midline. So remember the little trick for midline is you add them together and divide by 2. So midline, we're going to add 56 plus 24.2 and divide by 2. And when I did that, I got 40.1. Now this is going to represent something. This is going to represent our average annual temperature. So let's just write that. This is our average annual temperature. Pretty cool, 40.1 degrees. And go up to your graph once and let's draw that midline on at 40.1 and see if it actually looks right. Does that look correct? Does half look above and half look below? Yeah, I would say it does. Pretty cool. Continuing on, what is the period? Well, how often does this repeat? The period is every 12 months. The temperatures are going to start back over in January with cold temperatures and then make their way around. And finally, amplitude. So remember the trick for amplitude. Amplitude, you're going to take your max minus your min. So 56 minus 24.2 and then divide by 2. And so when you do that, you get 15.9. And that's going to be your amplitude. And you know what? We're going to need the K also for this equation, which we're going to write next. And so let's see if we can find K. Does this look like a sine or cosine curve versus like tangent or something like that? I think so. I think it looks like sine or cosine. So the period is 2 pi divided by K. Well, our period is 12 months. So 12 equals 2 pi divided by K. Solve it for K. Figure out what K is. Multiply by K. And then you have to get the 12 out of there. So divide by 12. These cancel. And you're going to have K equals 2 pi over 12 or pi over 6. Part C, find the sinusoidal function for the data using the sine curve. What that means is we have to write an equation with sine in it. Not cosine, but sine. Sine usually starts right on the midline and goes up. So in other words, this point right here is going to have to be our starting point because that's the part that's on the midline and goes up in that direction. So in other words, there's going to have to be a phase shift. Instead of starting at 0, it's over 1, 2, 3, 4. There's going to be a phase shift of 4. And this is going to be our vertical axis, basically, where we start from. So y equals a sine k x minus b plus d. Let's plug in what we know. It's going to go y equals a is 15.9. Does it need to be negative? No, because we're starting at the midline and going up, so it's not a reflection. So it's y equals 15.9. Sine, now we plug in our k, which is up here, pi over 6. Then a parenthesis, x minus b. B is the phase shift. Remember, we're shifting right 4. And so it's x minus 4. 4 is the b. And then it's plus d, and d is the midline. And remember, our midline is at 40.1. So 40.1. This crazy equation right here is the equation that represents the temperatures in Juneau, Alaska annually. And they can be represented with a sinusoidal sine curve. Pretty cool. Next, you guys, you're going to do Unit 3, Practice 5. And if you get stuck, just let us know. Otherwise, have a great day.